Let's look at an example of how we would choose a sample size based on the margin of error that we need. So suppose we want to calculate a 95% confidence interval for the mean height of adult male residents of St. Joseph. The mean height follows a normal distribution with standard deviation sigma equal to 3.94 inches. How large a sample would we need to estimate the mean height mu in this population to within plus or minus 1 with 95% confidence? All right, let's start with A. Let's start by identifying information that we know. So we know we want a 95% confidence interval. The confidence level tells us Z star, and this is one we can just look up in the table. Z star is 1.96. We also know that the mean height follows a normal distribution with standard deviation 3.94. And we want to measure the mean height to within plus or minus 1. This is going to be my M for margin of error. And the question is, how large a sample do I need? So I want N. All right, so I'm going to turn the page so I have a little more room. So we need to solve for N. And we know that Z star is 1.96. We know that the standard deviation is 3.94. And we know that the margin of error we want to be 1. Okay? So I'm going to solve. Well, margin of error is Z star times sigma over square root of n equals m. And what we want is that 1.96 times 3.94 over the square root of n is less than or equal to 1, right? We want to guarantee within 1. So our margin of error should be less than or equal to 1. And now we're just going to solve. I want to get the square root of n by itself, so I'm going to multiply by root n on both sides. It cancels on the left. I'm left with 1.96 times 3.94 is less than or equal to the square root of n. How do I get rid of square roots? I square both sides. So on the right I have n, and on the left I have 1.96 times 3.94 quantity squared. So make sure you use parentheses there and plug that into your calculator. I get 59.635 is less than or equal to n. Now n is my sample size, and so n has to be an integer. So we're always going to round up to the next integer. Regardless of what this decimal is, I always need to go up to the next integer. So my sample size n must be at least 60. All right, in part B, we want to know if we want a margin of error no more than 0.5 inches, how big a sample must we take? So the only thing that's changed in part B here is that the margin of error is no longer just less than or equal to 1. I want it less than or equal to a half. So we're going to solve 1.96 times 3.94 divided by the square root of n. And now we want the margin of error less than or equal to 1/2. So the first step is still the same. I'm going to multiply by the square root of n on both sides. So they cancel on the left. I'm left with 1.96 times 3.94 is less than or equal to 1/2 square root of n. And now to get rid of the 1/2, I'm going to multiply both sides by 2 over 1, which is just 2. So on the left, on the right they cancel. On the left, I have 2 times 1.96 times 3.94 is less than or equal to the square root of n. Let me go ahead and rewrite that. And now, since the square root of n is by itself on the right side, I'm going to square both sides. All right, so go ahead and plug that into your calculator. I get 238.54 is less than or equal to n. And again, remember that we're going to round up to the next integer. So n must be at least 239. All right, now look at this for a second. In part A, I wanted a margin of error less than or equal to 1. And in part B, I just wanted to cut that margin of error in half. Notice that to cut my margin of error in half, I had to take my sample size, which was 60, and basically quadruple it, right? 60 times 4 would be 240. So cutting my margin of error in half means that I have to quadruple my sample size, which in practice might be really difficult, right? Or really expensive. Let's look at one more example. A researcher recorded the times of 10 runners in a 100-meter sprint in the Olympic Games and found that they had a mean time of 9.76 seconds. It's known the standard deviation of times for all Olympic runners in the 100-meter sprint has a standard deviation of 0.07 seconds. And the researcher found a confidence interval for the mean time of all Olympic runners to be between 9.73 seconds and 9.79 seconds. How confident are you that this interval contains the true mean of all Olympic runners? All right, so again, let's identify what we know. So the researcher recorded the times of 10 runners. That's telling me that n is 10. And he found that the mean time is 9.76 seconds. So here's my x bar. We also know the population standard deviation is 0.07 seconds. And we know a confidence interval was computed to get 9.73 to 9.79 seconds. What do I want? I want to know how confident I am. So I'm looking for the confidence level C. All right, which in turn means that I don't know the critical value Z. All right, so let's plug in what we know. Well, we know that the formula for confidence interval is x equals plus or minus Z star times sigma divided by the square root of n. And in this case, the problem tells us that this is equal to 9.73 to 9.79. So let's just take this right one. That means that 9.79 must be equal to the sample mean plus or not plus or minus, just plus, right? Because that's how we get the upper bound, plus the critical value times the standard deviation over the square root of n. Let's plug in what we know. The mean was 9.76. We're looking for Z star. The standard deviation was 0.07 and n was 10. All right, so now I have an equation with one unknown, right? I'm looking for Z star. And so I'm just going to solve this equation. So I'm going to start by subtracting 9.76 from both sides. That gives me 0.03 equals Z star times 0.07 divided by the square root of 10. Now to get rid of a fraction, I'm going to multiply by its reciprocal. So I'm going to multiply both sides by square root of 10 divided by 0.07. And so what happens here? On the right, Well, on the left, I get z star. I'm going to switch sides here. And on the right, I just need to plug this into my calculator. So I have square root of 10 times 0.03 divided by 0.07. I'm going to round 2 decimal places, and that's going to give me 1.36. Okay, so now I know my critical value. How am I going to use that to find my confidence level? Well, it corresponds to a confidence level of C. If we find the area in the table, we'll have C over 2. So we're going to go to the table to find an area associated with 1.36, and I've got the table here. So 1.36, I'm going to look in the row for 1.3 and up to the column with 0.6. Here's the 0.6 column, and so here is the area, 0.4131. Okay, so 0.4131 is C divided by 2. And so if I want C, I just need to multiply both sides by 2. So C is 0.8262. And so now I can answer the question, how confident are we that this interval contains the true mean of all Olympic runners? Well, I'm going to convert this C to a percent. We're 82.62% confident that the true mean is in the interval. All right.